So one of the first videos that did really well on my channel was a video which I called A Very Interesting Differential Equation, where I found a solution to the differential equation f prime of x equals f inverse of x. Now there are a couple of things pretty interesting about this differential equation. One is the simplicity, and the other is the mixture of a derivative as well as something involved with composition. So really taking the inverse of a function is deeply connected to composing it with itself really and getting the identity function. And so differentiation and composition are two things that are pretty different, so combining them together in this problem is pretty interesting. And so you might say, well, where did I find this problem? So I was doing a research call with one of my collaborators, and while we were putting the finishing touches on a paper, he suggested that this would be a really interesting problem to look at. And so I'm really grateful for that suggestion. But today what I'd like to look at is a pretty interesting generalization of this problem. And I think it's pretty aesthetic, maybe not quite as aesthetic and simple as the original problem, but still quite nice. So it's going to involve a system of n differential equations, and for lack of a better word, they're compositional differential equations, in that they involve differentiation and inversion, which, like I said, is related to composition of functions. So the functions we're solving for will be enumerated f1, f2, f3, up to fn. And so we'll have f1 prime of x is f2 inverse of x. And then f2 prime of x is f3 inverse of x. f3 prime of x is f4 inverse of x, and so on and so forth. All the way down until we get fn minus 1 of x is fn inverse of x, and then we complete the loop. So fn prime of x is f1 inverse of x. So we loop it back around to the start. So this problem down here that we did in the previous video is pretty complicated, and we really just found one solution. We didn't prove it was the unique solution. And this system of equations, it would be very, very difficult to find a unique solution, but perhaps we could hack our way towards a solution. And so let's do that. And we'll do that by assuming we can get a solution which has a nice form. So let's do that. So let's assume that we have a solution which I'll call f1 of x equal a1 x to the r1, so it's like a power function, and then f2 of x is equal to a2 x to the r2, all the way up to fn of x is equal to an x to the rn, where these ai's and ri's are just numbers. Okay, great. And now let's impose these conditions over here. So let's note that in general we have fi prime of x is equal to ai times ri times x to the ri minus 1. Okay, but then what about the inverse? Well, we can pretty easily calculate the inverse. So fi inverse of x will be equal to x over ai to the 1 over ri power. So I'll let you work out the details, but that's fairly straightforward. Okay, so now we'll impose these equations. So let's start here at the top with this first equation. So we'll need f1 prime, but that will be a1 r1 times x to the r1 minus 1 equals f2 inverse. But that will be x over a2 to the 1 over r2. Okay, so we have that. Now let's move down the line. So the next one, which I'll have be this green dot, will be a2 r2 x to the r2 minus 1 equals x over a3 to the power 1 over r3. So that would be that next one. Now let's put this blue dot, and we'll have this as the blue equation right here. So we'll have A3 R3 x to the R3 minus 1 is equal to x over A4, and then to the power 1 over R4. Okay, nice. And now let's wrap it all the way up with this very last one down here, which I'll write in this purple dot color. So let's see, we'll have A sub n, R sub n, x to the Rn minus 1 is equal to x over A1 to the power 1 over R1. So we have something like that. So now let's notice that we get this system of equations for the R's and the A's. And what's important here is that the powers of x have to be the same on both sides. And that's probably the first thing to focus on. So we need the power of x here, which is R1 minus 1, to be the same thing as the power of x on this right-hand side of the equation, which is 1 over R2. Let's forget about the constants for now. We'll come back to the constants. So that gives us this equation, R1 minus 1 equals 1 over R2. Then we can do the same sort of thing equating these coefficients. So equating these powers. So we'll have R2 minus 1 equals 1 over R3. And then likewise for this next one, we'll have R3 minus 1 equals 1 over R4. All the way down to this very last one, which is Rn minus 1 equals 1 over R1. So that completes our list. And now let's notice that we have n equations and n unknowns. So we should be able to solve for all of the variables if we are careful. But it is a nonlinear system, so that makes it a little bit trickier. Okay, so now from here what I'd like to do is pair these off moving down and see if we can put everything in terms of R1. So hopefully that's not too bad. So first of all, this one right here tells us that R2 is equal to 1 over R1 minus 1. So that's just inverting the numerator and the denominator. And next up, we'll take this expression for R2 and we'll insert it into this equation for R2, and we'll solve for R3 in terms of R2. So let's see what we'll get. So starting, we'll have R3 is equal to 1 over R2 minus 1, but R2 can be written as 1 over R1 minus 1. Then we'll have minus 1 like that. Okay, so that's R3 in terms of R1. But we can simplify this quite a bit by multiplying the numerator and the denominator here by R1 minus 1. That makes it so that everything's a little bit nicer. So in the end, this is going to look like R1 minus 1, and then in the denominator we'll have 2 minus R1. Okay, and now we'll just descend down the line. So we'll take this expression for R3 and we'll plug it into this equation. So I won't go through all of the details. It's really just symbolic manipulation, if you will. But what we end up with is the following equation for R4 in terms of R1. So R4 is R1 minus 2 over 3 minus 2R1. So let's look at the next one. And again, I won't go through the explicit calculation, but it will involve plugging this R4 into the appropriate equation, which is in this case, R4 minus 1 equals 1 over R5. So that's going to lead us to see that R5 is indeed equal to 2 R1 minus 3 over 5 minus 3R1. Now I think things are shaping up. Look at all of these coefficients that we have. We've got coefficients 1, 2 in a couple of places. We have a coefficient of 3, we have a coefficient of 5. But what's true about the numbers 1, 2, 3, 5? Well, they're in fact the first Fibonacci numbers. So the Fibonacci numbers go like 1, 1, 2, 3, 5. So that's pretty cool. It seems like the Fibonacci numbers are showing up. And if you worked out more examples, you would see that you're getting exactly the Fibonacci numbers as the coefficients in these expressions of the higher r's in terms of R1. And so we could prove this by induction, but since this is a bit of an exploratory video, we won't worry about proving it with induction. We'll just jump to the following observation. We have Rn can be written in terms of R1 as the n minus second Fibonacci number times R1, and then minus the n minus first Fibonacci number. And this will be all over the nth Fibonacci number minus the n minus first Fibonacci number times R1. So we end up with something like that for R sub n. And perhaps the most important thing about this equation is it uses all of these expressions except for the very last one. So we have not used this one that I have in my yellow circle yet, which will indeed allow us to solve for R1 as a number, because between this green boxed equation and this yellow circled equation, we have a system of simply two equations and two unknowns. Okay, so I think we're off to a good start. Now let's start with these two equations and see what R1 is. So putting everything together from the last board, we determined that R sub n was this expression involving R1 and the Fibonacci numbers. And then we had our final equation, which was Rn minus 1 was 1 over R1. Let's recall the Fibonacci numbers real quick. They have the two seeds 1, so F1 and F2 are both 1. And then we have Fn is Fn minus 1 plus Fn minus 2. And also sometimes you take the 0th Fibonacci number to be 0, just by the way. Okay, so from here what we'll do is put these two equations together and see where we go. So we'll have Rn minus 1 is 1 over R1, but I'll take Rn and rewrite it like this. So we'll have Fn minus 2 times R1 minus Fn minus 1 over Fn minus Fn minus 1 R1 equals 1 over R1 plus 1. That's for moving this 1 over. Great. But now from here, I'm going to give this a common denominator. So I'll think of that 1 as R1 over R1. So I'll rewrite this as R1 plus 1 over R1. Okay, so that's good. Now let's cross multiply and so see what we get. So we'll have Fn minus 2 times R1 squared minus Fn minus 1 times R1. So that's from multiplying here and here. And then multiplying this up here, what will we have? Well, we'll have minus Fn minus 1 R1 squared. So that's the R1 squared term. And then we'll have two R1 terms. We'll have minus Fn minus 1 R1 from this term times 1, and then we'll have Fn times R1. So that'll be plus Fn times R1. Then finally, we've got a constant term, which is simply Fn, so plus Fn. Okay, so this is looking good. Now let's cancel some things. We have this minus Fn minus 1 R1 here, and on the other side of the equation. We can simplify those. Okay, that's good. Then we can start moving some things around. So in fact, what I'd like to do is take this term, this minus Fn minus 1 R1 squared, and move it over here. And that'll leave us with Fn minus 1 plus Fn minus 2 times R1 squared equals Fn R1 plus Fn. Great. But look at this. This is exactly the recursion for the Fibonacci numbers. So we can replace everything in this magenta box with simply Fn. But now notice everything on the right and the left-hand side of the equation has a factor of Fn, which means we can divide by that, leaving us with R1 squared equals R1 plus 1. But that's exactly the quadratic equation that the golden ratio satisfies. Well, there are two solutions to this quadratic equation, but we'll take the golden ratio solution, which we'll call phi. So we have R1 equals phi, but let's just recall that as 1/2 1 plus the square root of 5. Okay, so now we've got R1, so now let's see what that tells us about our other exponents. So we just determined our first exponent, our R1, where recall F1 was assumed to be of the form A1 times x to the R1, and it was the golden ratio, which recall that is 1/2 times the quantity 1 plus the square root of 5. Let's also recall that it satisfies the equation phi squared equals phi plus 1. Now let's use this value of R1 to determine the value of R2, R3, R4, so on and so forth. Okay, so let's just plug R1 into this. So we have phi minus 1 is equal to 1 over R2. So taking the reciprocal of both sides, we get R2 is 1 over phi minus 1. But now we can actually simplify this down to something quite a bit nicer. Let's multiply the numerator and the denominator by phi plus 1. So in the denominator, or in the numerator, we'll have phi plus 1, which is phi squared, by this relationship that the golden ratio satisfies. And then in the denominator, by multiplying things out, difference of squares formula, we'll have phi squared minus 1. But now taking this equation, phi squared equals phi plus 1, that tells us phi squared minus 1 is simply phi. So this gives us phi squared over phi, which is phi. So that means in the end, what's the value of R2? Well, it's simply phi as well. It's also the golden ratio. But then, since this relationship is pervasive all the way down, that tells us that all of these exponents are the golden ratio. So in fact, we have R1 equals R2 equals R3 equals all the way up to Rn. They are all equal to this number phi. And also importantly is that if we had chosen the other root of that quadratic equation, they would all be equal to the other root. So they all have to be equal to each other regardless of which root we chose. In this case, we just chose the root with the plus sign right here. Okay, so now that we've got these exponents, let's see if we can do something about those coefficients. So we determined that all of our exponents for our solution are simply this golden ratio phi, then extracting coefficients from that set of equations that we had on the board, and then simplifying using some rules that are satisfied by phi, we get the following set of equations for the coefficients. Remember, those were all a sub I, or they were notated by a sub I. So we have a1 times phi is the same thing as a2 to the power phi minus 1. We have a2 times phi is equal to a3 to the power of phi minus 1, all the way down here where it loops back on itself. And we have an times phi is a1 to the phi minus 1. Now, I'll just say that I don't think it's super interesting to look at this general case, because nothing like pretty comes out of it. Like the general case for the exponents was quite pretty. All of those exponents had to be the same. But here the coefficients get just more complicated and more complicated and more complicated. So that being said, what we will do is focus on the n equals 2 case. Notice the n equals 1 case is the one that was in that previous video. Okay, so here I'll use the following notation. I'll set a1 equal to a and a2 equal to b. So that means we don't need subscripting. That means this blue boxed set of equations turns into a1 or a times phi is equal to b to the power phi minus 1. And then we'll have b times phi is equal to a to the power phi minus 1. Okay, so let's get at it. So this second equation will tell us that b is equal to 1 over phi. Let's recall that 1 over phi was the same thing as phi minus 1. We in fact use that right here. It's phi minus 1 times a to the phi minus 1. And now we will take this expression for b and plug it into the above equation. And let's see what that leaves us with. We will have a times phi is equal to phi minus 1 times a to the phi minus 1, all to the power phi minus 1. Okay, so let's simplify this as much as we can. We have a times phi is phi minus 1 to the power phi minus 1 times a to the power phi squared minus 2 phi plus 1 using exponent rules is equal to a to the phi squared minus 2 phi plus 1 using exponent rules. Okay, so now let's divide this a over, and then we'll divide this phi minus 1 to the phi minus 1 over. That'll leave us with a to the power phi squared minus 2 times phi is equal to phi minus 1 to the power phi minus 1 over phi. But let's recall that that phi in the denominator is the same thing as having a phi minus 1 in the numerator, because 1 over phi is phi minus 1. So that turns this into phi minus 1 to the power phi. Now I'd like to simplify this exponent a little bit. So I'll put a red box around that, and then we'll simplify the exponent here, using the fact that phi squared is the same thing as phi plus 1. So this turns into phi plus 1 minus 2 phi. Or in other words, it turns into 1 minus phi. So now we'll take the 1 minus phi-th root of both sides, and that'll leave us with something like a equals phi minus 1 to the power phi over 1 minus phi. But 1 over 1 minus phi can be written as minus phi. Then putting this all together, we have this is phi minus 1 to the minus phi squared. And that's our value for a. And then from there, we can easily calculate our value for b using perhaps this equation right here. But I'll leave that as a homework exercise. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.